Imagine, just for a moment, that you are standing on the edge of everything you have ever known. Behind you lies the Earth, that tiny, fragile, blue marble spinning quietly in the darkness of space. Behind you lies every memory, every civilization, every breath ever taken by every human being who has ever lived. And in front of you, stretching out into an abyss so vast that your mind physically cannot comprehend it, lies the Milky Way galaxy. A swirling ocean of 400 billion stars, trillions of planets, and mysteries so deep that even the greatest minds in the history of our species have barely scratched the surface. Now, imagine that someone hands you the keys to the most powerful spaceship ever constructed. Not a spaceship built with today's technology, not something limited by our current understanding of engineering or physics, but the absolute pinnacle of what any civilization could ever build. A ship powered by the energy of stars, capable of traveling at velocities that would make our fastest rockets look like snails crawling across a continent. You climb aboard this magnificent vessel, you point it toward the edge of the Milky Way, you fire the engines, and you fly. You fly, and you fly, and you fly. You fly for years, you fly for centuries, you fly for millennia. And the question that this entire video is built around, the question that will take us on a journey through the deepest, most mind-bending corners of physics, cosmology, philosophy, and the very nature of reality itself, is simply this: will you ever escape? Will you ever cross that invisible boundary between our galaxy and the great beyond? Will you ever reach another galaxy, another island of stars in the infinite cosmic ocean? And the answer, my friends, the answer that we are going to explore in extraordinary detail over the course of this video, is no. You will not escape. Humanity will never escape the Milky Way. And the reasons why are not just surprising. They are not just fascinating. They are genuinely, deeply, profoundly terrifying. Because it is not our technology that fails us. It is not our ambition that falls short. It is the universe itself, the very fabric of space and time, the fundamental laws of physics that govern every atom and every photon and every quantum of energy in existence, that have conspired to build a prison so vast, so elegant, so utterly inescapable that no civilization, no matter how advanced, no matter how intelligent, no matter how many millions or billions of years they have had to develop their technology, can ever break free. Now, before we dive into the depths of this cosmic prison, before we peel back layer after layer of physics and astronomy and mathematics to reveal just how thoroughly we are trapped, let me give you a taste of what is coming. Let me plant some seeds of curiosity in your mind that will grow into full understanding as this video unfolds. Did you know that the Milky Way galaxy is moving through space at a speed of approximately 2.1 million kilometers per hour? That is not a typo. 2.1 million kilometers every single hour. And yet, despite this incredible velocity, we are not moving toward freedom. We are moving toward a collision with our nearest large galactic neighbor, the Andromeda galaxy, a crash that will happen in approximately 4.5 billion years and will reshape our entire galactic home. But here is the twist. Even that collision, even the merger of two entire galaxies containing hundreds of billions of stars each, will not set us free. It will only make our prison larger. Did you know that 94% of the observable universe, 94% of everything we can see with our most powerful telescopes, every galaxy, every star, every planet in that vast majority of the cosmos, is already permanently unreachable? Not unreachable because we lack the technology, not unreachable because we haven't tried hard enough. Unreachable because the space between us and those objects is expanding faster than the speed of light. And no matter what we do, no matter how fast we travel, we can never, ever catch up. Did you know that scientists have calculated that in roughly 100 billion years, every single galaxy outside our local neighborhood will have vanished from the sky? Not destroyed, not hidden, but carried so far away by the expansion of space that their light will never reach us again. Future civilizations, if they exist that far in the future, will look up at the night sky and see nothing but their own galaxy. They will have no evidence that the universe was ever anything more than a single island of stars floating in an infinite void. They will not know about the Big Bang. They will not know about the expansion of the universe. They will not know they are in a prison. And perhaps most haunting of all, did you know that even if an alien civilization exists somewhere in the universe, a civilization millions or even billions of years more advanced than us, a civilization with technology so sophisticated that it would appear to us as pure magic, even they cannot escape? The laws of physics do not bend for intelligence. The expansion of the universe does not slow down for ambition. The cosmic speed limit does not make exceptions for civilizations that really want to explore. Every intelligent species in the universe, if there are any others out there, is trapped in the same way we are. Every single one of them is stuck on their own galactic island, watching the rest of the universe slowly fade away. If any of what I have just said has sparked something in your mind, if you feel that tingle of curiosity, that itch to understand, that deep human need to know why, then you are in exactly the right place. Because over the course of this video, we are going to explore this topic in a way that very few people have ever attempted. We are going to start from the very basics, from the size of our planet and our solar system, and we are going to zoom out, step by step, scale by scale, until we are staring at the entire observable universe and understanding, truly understanding, why we are trapped within it. We are going to dive deep into Einstein's theory of relativity and understand why nothing can travel faster than light. We are going to explore the expansion of the universe and understand how space itself can grow faster than any object can move through it. We are going to confront dark energy, the most mysterious and powerful force in the cosmos, and understand how it is accelerating our imprisonment with every passing second. We are going to examine the local group, our cosmic neighborhood, and understand why it represents the absolute maximum boundary of humanity's possible reach. We are going to journey into the far future, billions and trillions and even Googles of years from now, and witness the slow, inevitable heat death of the universe, the final proof that escape was never possible. We are going to examine every possible escape route that science has ever imagined, from warp drives to wormholes, from generation ships to digital consciousness, and we are going to understand why each and every one of them ultimately fails. We are going to ask whether alien civilizations face the same predicament, and what that means for the Fermi paradox and the search for extraterrestrial intelligence. And finally, we are going to grapple with the deepest philosophical question of all. If we are truly trapped, if the Milky Way is our permanent home, what does that mean for the human spirit? Is it cause for despair, or could it be in some profound and beautiful way a source of wonder? So buckle up, my friends. Subscribe to this channel if you have not already. Hit that like button because it genuinely helps more people discover content like this, and settle in for one of the deepest, most comprehensive explorations of our cosmic imprisonment that you will ever encounter. Let us begin. To understand why humanity will never escape the Milky Way, we first need to understand something fundamental. We need to understand scale. We need to understand just how incomprehensibly, absurdly, mind-breakingly enormous the universe actually is. Because here's the thing about human beings. We evolved on the plains of Africa, chasing animals and gathering berries, and our brains were shaped by that experience. Our intuitive sense of distance, the sense that tells us that the next village is far away, or that the mountain on the horizon is very far away, was calibrated for a world measured in kilometers, maybe hundreds of kilometers at most. We have no intuitive grasp of the distances involved in space. When someone tells you that the moon is 384,000 kilometers away, that number means almost nothing to your brain. You can say it, you can write it down, you can nod and pretend to understand, but you cannot feel it. You cannot hold it in your mind the way you can hold the distance from your house to the grocery store. And the moon is the closest thing to us in all of space. It is literally our next-door neighbor, the closest celestial body to Earth. And already, at just 384,000 kilometers, we are pushing the limits of human intuition. So let us start there. Let us start with the moon and build outward, step by step, until the true scale of our prison reveals itself. The moon orbits Earth at an average distance of 384,400 kilometers. Light, the fastest thing in the universe, traveling at 299,792 kilometers per second, covers this distance in about 1.3 seconds. When you look at the moon on a clear night, you are seeing it as it was 1.3 seconds ago. That is not very long. That is barely noticeable. Now, let us take the next step. The sun, that enormous ball of nuclear fire that gives us warmth and light and life, is about 150 million kilometers from Earth. At the speed of light, this distance takes 8 minutes and 20 seconds to cross. So when you look at the sun, you are not seeing it as it is now. You are seeing it as it was 8 minutes and 20 seconds ago. If the sun were to suddenly vanish, we would not know for over 8 minutes. We would continue to feel its warmth, continue to see its light, for 8 minutes and 20 seconds after it had already ceased to exist. Already, at the scale of our own solar system, the distances are large enough to introduce meaningful delays even for light, the fastest thing there is. But the sun is just one step on our journey outward. Let us go further. Let us travel to the outer reaches of our solar system. Beyond the orbit of Neptune, the most distant major planet, lies a vast, cold, empty region of space. The Kuiper Belt, home to Pluto and millions of other icy objects, extends from about 30 to 50 astronomical units from the Sun, where 1 astronomical unit is the distance from the Earth to the Sun. Beyond the Kuiper Belt lies an even more remote region called the Oort cloud, a hypothetical shell of icy objects that may extend up to 2 light-years from the Sun. 2 light-years. That means that light, starting from the Sun, would take 2 entire years to reach the outer boundary of our solar system's gravitational influence. And we are still talking about our own solar system. We have not even begun to discuss the distances between stars. To put the size of our solar system in some kind of perspective, consider Voyager 1, launched by NASA on September 5, 1977. Voyager 1 is the most distant human-made object in existence. It has been traveling through space for nearly half a century, moving at approximately 17 kilometers per second, which is about 61,000 kilometers per hour. That is incredibly fast by human standards. It is faster than any bullet, faster than any jet, faster than anything most people will ever experience. And yet, after almost 50 years of continuous travel, Voyager 1 has covered a distance of about 24 billion kilometers. That sounds like a lot, and it is, but in terms of the distance to even the nearest star, it is almost nothing. If Voyager 1 were heading toward Proxima Centauri, the closest star to our Sun, it would take approximately 73,000 years to arrive. 73,000 years. Human civilization, from the first cities in Mesopotamia to the smartphone in your pocket, spans roughly 10,000 years. Voyager would need 7 times the entire duration of human civilization just to reach the nearest star. And it would still be inside the Milky Way. It would have covered a distance so tiny compared to the size of the galaxy that it would not even register on a galactic map. Let us now talk about that nearest star, Proxima Centauri, because it helps us understand the true emptiness of space. Proxima Centauri is a small, dim red dwarf star in the Alpha Centauri system, and it lies approximately 4.24 light-years from our Sun. 4.24 light-years. That means light, traveling at its maximum possible speed, takes over 4 years to make the journey. To help you grasp what this distance actually means, let us use an analogy. Imagine that you shrink the Sun down to the size of a basketball. In this model, the Earth would be a tiny grain of sand about 26 meters away. Jupiter would be a marble about 135 meters away. Neptune would be a small pebble about 800 meters away. And Proxima Centauri? In this model, where the Sun is a basketball, the nearest star would be another smaller ball about 6,500 kilometers away. That is roughly the distance from New York City to Los Angeles and back. Imagine a basketball sitting in a park in New York, and the nearest other ball is somewhere in Hawaii. That is how empty space is. That is how far apart even the closest stars are. And remember, we are still talking about the nearest star. The Milky Way contains between 100 and 400 billion stars, most of them vastly more distant than Proxima Centauri. Now, let us zoom out further. Let us look at the Milky Way galaxy as a whole, the structure that serves as both our cosmic home and our cosmic prison. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure made of stars, from which spiral arms extend outward like the arms of a pinwheel. The galaxy is enormous. Its disk is approximately 100,000 light-years in diameter, though some recent estimates suggest it may be closer to 200,000 light-years across when you include the fainter outer regions. The disk is relatively thin, roughly 2,000 light-years thick, giving the galaxy a shape somewhat like a fried egg or a thin disk when viewed from the side. At the very center of the Milky Way lies a supermassive black hole called Sagittarius A star, which has a mass of approximately 4 million times the mass of our Sun. This black hole, despite its enormous mass, is tiny compared to the galaxy itself, occupying a region of space smaller than the orbit of Mercury. But its gravitational influence helps shape the orbits of stars in the galactic center, and it serves as the gravitational anchor around which the entire galaxy rotates. Our Sun is located in one of the galaxy's spiral arms, known as the Orion Arm or the Orion Spur, approximately 26,000 light-years from the galactic center. We are not at the center of the galaxy, nor are we at the edge. We are somewhere in the middle suburbs, if you will, orbiting the galactic center at a speed of about 220 kilometers per second. Even at this speed, it takes our solar system approximately 230 million years to complete one orbit around the galaxy. This period is sometimes called a galactic year. Since the Sun formed about 4.5 billion years ago, it has completed roughly 20 orbits of the galaxy. In the entire history of our star, it has gone around the galaxy only 20 times. The total mass of the Milky Way is estimated to be about 1.5 trillion times the mass of our Sun. But here is something that should immediately make you pause. Most of that mass is not in the form of stars. Most of it is not in the form of planets or gas or dust or anything we can see or touch or detect with ordinary instruments. Most of the mass of the Milky Way is dark matter, a mysterious substance that does not interact with light, does not emit any radiation, and can only be detected through its gravitational effects on visible matter. We know dark matter is there because without it, the galaxy would not hold together. The stars in the outer regions of the galaxy are orbiting so fast that, based on the visible mass alone, they should fly off into intergalactic space. Something invisible is providing extra gravitational pull, holding the galaxy together. That something is dark matter, and it forms a vast, invisible halo surrounding the visible disk of the Milky Way, extending hundreds of thousands of light years in every direction. So when we talk about the Milky Way as our prison, we are not just talking about the visible disk of stars. We are talking about an enormous, mostly invisible structure of dark matter, within which the visible galaxy is embedded, a structure far larger than the starry disk we see in photographs. Now, let us do some math because the numbers are crucial to understanding why escape is impossible. The Milky Way is 100,000 light-years across at minimum. That means that light, the fastest thing in the universe, takes 100,000 years to cross from one side of the galaxy to the other. 100,000 years. Let me put that in perspective. 100,000 years ago, modern humans had only recently migrated out of Africa. Neanderthals still walked the earth. Agriculture had not been invented. Writing had not been invented. Cities, nations, technology, science, all of it lay in the unimaginable future. And in that entire span of time, a beam of light would only have crossed from one side of our galaxy to the other. That is how big the Milky Way is. Now, what if we sent a spacecraft across the galaxy? Not at the speed of light because we cannot travel at the speed of light, but at some fraction of it. Let us be optimistic. Let us say that humanity develops the technology to travel at 10% the speed of light. That is 30,000 kilometers per second, far beyond anything we can currently achieve. At that speed, crossing the Milky Way would take 1 million years. 1 million years. Our species, Homo sapiens, is only about 300,000 years old. We would need more than 3 times the entire existence of our species just to cross our own galaxy. And what about more realistic speeds? At the speed of Voyager 1, crossing the Milky Way would take approximately 1.7 billion years. Billion, with a B. That is roughly a third of the age of the Earth itself. These numbers should make one thing abundantly clear. Even ignoring everything else, even ignoring the expansion of the universe and dark energy and all the other barriers we are going to discuss, the sheer physical size of the Milky Way alone represents an almost insurmountable challenge. But the Milky Way is not even the barrier we are ultimately worried about. The Milky Way is our home. The real question is whether we can leave it and reach somewhere else. And to understand why we cannot, we need to understand what lies beyond the Milky Way and how far away it is. The nearest large galaxy to the Milky Way is the Andromeda galaxy, also known as Messier 31 or M31. Andromeda is a spiral galaxy somewhat larger than the Milky Way, containing approximately 1 trillion stars. It lies at a distance of approximately 2.5 million light-years from us. 2.5 million light-years. Try to hold that number in your mind. If crossing the Milky Way at light speed takes 100,000 years, reaching Andromeda at light speed takes 2.5 million years. At 10% the speed of light, the journey would take 25 million years. At Voyager speed, it would take over 40 billion years, roughly 3 times the current age of the universe. The distances between galaxies are on an entirely different scale than the distances within galaxies. We have gone from light years between stars to millions of light years between galaxies. Each step outward multiplies the distances by enormous factors, and with each multiplication, the dream of escape becomes more and more impossible. But Andromeda is actually one of the closest galaxies to us. There are galaxies far, far more distant. The observable universe, the portion of the universe from which light has had time to reach us since the Big Bang, has a diameter of approximately 93 billion light-years. Within this observable universe, there are an estimated 2 trillion galaxies. 2 trillion, that is 2,000 billion. Each of those galaxies contains anywhere from millions to trillions of stars. The total number of stars in the observable universe is estimated to be around 200 sextillion, that is 2 followed by 23 zeros. And the observable universe is almost certainly not the entire universe. The actual universe may be infinitely large, stretching out forever in every direction, filled with galaxies and stars and planets that we can never see and never reach, because their light has not yet had time to arrive. The scale is not just large. It is beyond any word in any human language. It is beyond imagination itself. And within this incomprehensible vastness, we are stuck on one small planet, in one small solar system, in one medium-sized galaxy, looking out at an ocean of light that we can see but never touch. The question is, why? Why are we so thoroughly, so completely, so fundamentally trapped? And the answer begins with a man named Albert Einstein, and a theory he published in 1905 that changed everything we thought we knew about the universe. The speed of light is not just a number. It is not just a measurement. It is a fundamental property of the universe, woven into the very fabric of space-time itself. And understanding why it represents an absolute, unbreakable barrier to our escape from the Milky Way requires us to understand one of the most important and counterintuitive theories in the history of science, Einstein's theory of special relativity. In 1905, a 26-year-old patent clerk named Albert Einstein published a paper titled On the Electrodynamics of Moving Bodies. This paper, one of 4 groundbreaking papers Einstein published that year in what is sometimes called his miracle year, laid out the theory of special relativity, and it was built on 2 simple postulates. The first postulate states that the laws of physics are the same for all observers who are moving at a constant velocity relative to each other. The second postulate states that the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. That second postulate is the one that changes everything. It sounds simple, almost innocuous, but its implications are staggering. If the speed of light is the same for everyone, no matter how fast they are moving, then our intuitive understanding of how speeds add up must be wrong. In everyday life, if you are on a train moving at 100 kilometers per hour, and you throw a ball forward at 50 kilometers per hour, the ball moves at 150 kilometers per hour relative to the ground. Speeds add up. But with light, this does not work. If you are on a spaceship moving at 90% the speed of light and you turn on a flashlight pointing forward, the light from that flashlight does not travel at 190% the speed of light relative to someone standing still. It travels at exactly the speed of light, 100%, not 1% more. This seemingly impossible fact has profound consequences, and those consequences are what make escaping the Milky Way impossible. The first consequence is that as an object accelerates and approaches the speed of light, its mass increases. Not its rest mass, the mass it has when it is standing still, but its relativistic mass, the effective mass it has in the frame of reference of a stationary observer. As a spaceship approaches the speed of light, its relativistic mass grows, and it does not just grow a little, it grows toward infinity. As the ship gets closer and closer to light speed, its mass gets larger and larger, requiring more and more energy to accelerate it further. And here is the crucial point. To actually reach the speed of light, the ship's mass would become infinite, and the energy required to push it would also become infinite. Since infinite energy does not exist, reaching the speed of light is not just difficult. It is not just impractical. It is physically impossible for any object with mass. This is not a limitation of our technology. This is not something we can overcome with better engines or more fuel. This is a fundamental law of the universe, as absolute and unbreakable as the law of gravity or the conservation of energy. No matter how advanced our technology becomes, no matter how much energy we can generate, no matter how clever our engineering, we cannot accelerate a massive object to the speed of light. Period. And since every spaceship, every human being, every atom of matter has mass, this means we can never travel at the speed of light. We are permanently, irrevocably limited to speeds below it. Now, you might be thinking, okay, so we cannot reach the speed of light. But can we get close? Can we travel at 90%, or 99%, or 99.99% of the speed of light? In principle, yes. There is no physical law that prevents us from getting arbitrarily close to light speed. But the energy requirements grow exponentially as you approach that limit. Let me give you some numbers to illustrate this. To accelerate a 1,000 kilogram spacecraft to 50%, the speed of light would require an amount of energy equivalent to approximately 2.8 times 10 to the 19th joules. That is roughly equivalent to the total energy output of the entire United States for about 3 months. To accelerate the same spacecraft to 90%, the speed of light would require about 5 times more energy than that. To get to 99% would require about 7 times the energy needed for 50%. And to get to 99.99% would require roughly 70 times the energy needed for 50%. The closer you get to light speed, the more energy each additional fraction of a percent requires. It is like climbing a hill that gets steeper and steeper as you approach the top, until at the very peak, the hill becomes a vertical cliff of infinite height. You can climb higher and higher, but you can never reach the top. And remember, these calculations are for a 1,000 kilogram spacecraft. That is tiny. A real interstellar vessel, one capable of carrying humans, life support systems, fuel, food, water, radiation shielding, and all the other necessities of a long journey through space, would have a mass of thousands or millions of tons. The energy required to accelerate such a vessel to even a small fraction of the speed of light is staggering. To accelerate a vessel with a mass of 100,000 tons to 10%, the speed of light would require energy equivalent to roughly the total energy output of our Sun for an entire second. And the Sun outputs 3.8 times 10 to the 26th watts. That is an almost incomprehensible amount of energy, far beyond anything humanity currently produces or is likely to produce for centuries or millennia to come. But the energy problem is even worse than it first appears, because of something called the rocket equation. In order to accelerate, a rocket must expel propellant out of its back end. The faster it expels the propellant, the more efficient the rocket is. But here is the catch. The propellant itself has mass, and that mass needs to be accelerated along with the rest of the spacecraft until it is used. So, to carry more propellant, you need more propellant to carry the propellant, which requires more propellant to carry that propellant, and so on. This is the tyranny of the rocket equation, first described by Konstantin Tsiolkovsky in 1903, and it means that the amount of fuel needed for a journey increases exponentially with the desired change in velocity. For interstellar velocities, the numbers become absurd. To accelerate a payload to 10% the speed of light using a fusion-powered rocket with an exhaust velocity of 5% the speed of light, you would need a mass ratio of about 7 to 1. That means for every kilogram of payload, you need 7 kilograms of fuel. That is manageable. But to reach 50% the speed of light with the same engine, the mass ratio jumps to about 150 to 1. For every kilogram of payload, 150 kilograms of fuel. And to reach 90% the speed of light, the mass ratio becomes about 8,000 to 1. You need 8,000 kilograms of fuel for every kilogram of payload. For a spaceship weighing 1,000,000 kilograms, you would need 8 billion kilograms of fuel. That is 8 million tons. And this is with a fusion engine, one of the most efficient propulsion systems conceivable. With chemical rockets, the kind we use today, the numbers are so absurd that they are not even worth calculating. You would need more fuel than there is matter in the observable universe. There is another consequence of special relativity that is worth exploring here, because it offers what appears to be a glimmer of hope, but ultimately turns out to be a false promise. That consequence is time dilation. According to special relativity, time passes more slowly for objects that are moving at high speeds relative to a stationary observer. This is not a theoretical prediction that has never been tested. It is an observed, measured, experimentally verified fact. Atomic clocks flown on high-speed aircraft run slightly slower than identical clocks left on the ground. Particles created in accelerators live longer when they are moving at high speeds. GPS satellites must account for time dilation in their calculations, or they would give incorrect positions. Time dilation is real, and at speeds close to the speed of light, its effects become dramatic. If you were traveling at 90% the speed of light, time would pass about 2.3 times more slowly for you than for someone standing still. At 99% the speed of light, it would pass about 7 times more slowly. At 99.99%, it would pass about 71 times more slowly. So, could time dilation save us? Could we travel at near light speed and experience only a few years of subjective time while the universe ages tens of thousands or millions of years around us? In theory, yes. If you could somehow accelerate to 99.99% the speed of light, a journey to Andromeda that takes 2.5 million years in the frame of reference of Earth would take only about 35,000 years in your frame of reference. At 99.9999%, it would take only about 1,100 years. And if you could get even closer to light speed, the subjective travel time could be reduced even further. But here is why time dilation does not actually help. First, the energy requirements for reaching such extreme velocities are, as we have already discussed, completely impractical. Second, even if you could achieve such speeds, the journey from the perspective of the rest of the universe still takes millions of years. When you arrive at Andromeda, 2.5 million years will have passed on Earth. Everyone you knew, every civilization you left behind, every trace of the world you departed from will be gone. Dust, not even a memory. You would step out of your spaceship into a galaxy where millions of years of events have unfolded without you, where Earth may not even be habitable anymore, where the human species may have evolved beyond recognition or gone extinct entirely. Time dilation does not cheat the universe. It does not compress the distance. It merely shifts the burden of time from the traveler to everyone else. And it comes with a terrible price: complete and irrevocable isolation from everything you have ever known. Third, and most importantly, time dilation does nothing to overcome the real barrier to escape, which is not the travel time, but the expansion of the universe. Even if you could travel at 99.9999% the speed of light, you still cannot outrun the expansion of space. And it is that expansion, not the speed limit alone, that truly traps us. This is where our story takes its most dramatic and terrifying turn. This is where we leave the realm of rockets and velocities and enter the realm of cosmology, the science of the universe as a whole. And what cosmology tells us about our prison is far more disturbing than anything the speed of light alone could suggest. In 1929, an American astronomer named Edwin Hubble made one of the most important discoveries in the history of science. working at the Mount Wilson Observatory in California, Hubble was studying distant galaxies and measuring their light. Specifically, he was looking at how the light from these galaxies was shifted toward the red end of the spectrum, a phenomenon known as redshift. Redshift occurs when the source of light is moving away from the observer. Just as the siren of an ambulance sounds lower in pitch as it drives away from you, the light from an object moving away from you is shifted toward lower frequencies, toward the red end of the visible spectrum. What Hubble discovered was remarkable. Almost every galaxy he observed was redshifted. Almost every galaxy in the universe was moving away from us. And not just that. The farther away a galaxy was, the faster it was receding. Hubble formulated this relationship as a simple mathematical equation, V equals h0 times d, where V is the recession velocity of the galaxy, d is its distance from us, and h0 is a constant now called the Hubble constant. This relationship, known as Hubble's law, told us something extraordinary about the universe. It is expanding. The universe is getting bigger. Every moment that passes, the distances between galaxies are increasing, and the farther apart two galaxies are, the faster the distance between them grows. Now, this is where things get really important, and where many people, even educated people, get confused. The expansion of the universe is not galaxies flying apart through space. It is not like an explosion where debris is scattered in all directions through a pre-existing void. It is space itself that is expanding. The fabric of space-time, the underlying structure within which all matter and energy exist, is stretching. New space is literally being created between galaxies. Imagine drawing dots on the surface of a balloon, then inflating the balloon. As the balloon expands, every dot moves away from every other dot. Not because the dots are moving across the surface of the balloon, but because the surface itself is growing. The distance between any two dots increases at a rate proportional to the distance between them. Dots that are far apart move away from each other faster than dots that are close together. This is an excellent analogy for the expansion of the universe, with the dots representing galaxies and the surface of the balloon representing the fabric of space. The key insight is that this expansion is happening everywhere, at every point in space, simultaneously. There is no center of the expansion. Every point in the universe sees every other point receding, and the rate of recession increases with distance. This has a mind-bending consequence. Because the rate of expansion increases with distance, there must exist a distance at which the rate of expansion equals the speed of light. Beyond this distance, space is expanding faster than light can travel through it. This boundary is called the Hubble sphere, and its current radius is approximately 14.4 billion light-years. Beyond the Hubble sphere, the recession velocity of galaxies exceeds the speed of light. Now, wait, does that mean those galaxies are moving faster than light? And does that violate Einstein's special relativity? The answer to the first question is yes, in a sense. The distance between us and those galaxies is increasing at a rate greater than the speed of light. But the answer to the second question is no. Special relativity says that nothing can travel through space faster than the speed of light. But the expansion of the universe is not travel through space. It is the expansion of space itself. General relativity, Einstein's broader theory of gravity and space-time, allows space to expand at any rate. There is no speed limit on the expansion of space, only on the motion of objects through space. This distinction is absolutely critical to understanding why we are trapped. Objects do not need to be moving through space to recede from us. Space itself is carrying them away, and because there is no limit on how fast space can expand, there is no limit on how fast distant objects can recede. They can, and do, recede faster than light, and we can never reach them. The observable universe, the region of space from which light has had time to reach us since the Big Bang 13.8 billion years ago, has a radius of approximately 46.5 billion light-years in terms of current distance. You might wonder how the observable universe can be larger than 13.8 billion light-years if the universe is only 13.8 billion years old, and light can only travel at the speed of light. The answer is precisely the expansion we have been discussing. Light from the most distant objects we can see was emitted when those objects were much closer to us. Since then, the expansion of space has carried those objects far away, to their current distances of about 46 billion light-years. The light traveled through expanding space, gaining extra distance from the expansion itself. This means the observable universe is much larger than the naive estimate of 13.8 billion light-years. It is a sphere with a diameter of about 93 billion light-years. But here is the truly disturbing part. Even though we can see objects up to 46.5 billion light-years away, we cannot reach most of them. Not now, not ever. Because the universe is not just expanding, it is accelerating. And this brings us to the most important and most terrifying concept in this entire discussion: the cosmic event horizon. Just as a black hole has an event horizon, a boundary beyond which nothing can escape, the accelerating expansion of the universe creates a cosmic event horizon, a boundary beyond which nothing we send out, not a spaceship, not a beam of light, not a radio signal, not anything, can ever reach. The cosmic event horizon is currently estimated to be at a co-moving distance of about 16 billion light-years. Any object currently beyond this distance, any galaxy, any star, any planet, is permanently, irrevocably out of reach. If you sent a beam of light toward one of those objects right now, the expansion of space would carry the object away faster than the light could approach it. The light would travel forever and never arrive, and the cosmic event horizon is not static. Because the expansion of the universe is accelerating, the cosmic event horizon is effectively shrinking in terms of what we can newly reach. Every moment that passes, more galaxies cross beyond the cosmic event horizon, leaving our possible future forever. They are not destroyed. They do not cease to exist. They simply become as unreachable as the other side of a black hole's event horizon. They are still there, still real, still made of stars and planets and possibly even life, but they are gone from us, separated by an ever-growing gulf of expanding space that no speed, no technology, no amount of time can bridge. Let us now quantify just how trapped we are. Of the estimated 2 trillion galaxies in the observable universe, how many are still theoretically reachable? The answer, calculated by cosmologists, is approximately 6%. Only about 6% of the galaxies we can currently observe are still within our cosmic event horizon, still theoretically accessible if we could travel at the speed of light starting right now. The other 94% are already gone, already beyond the boundary, already receding faster than light, already permanently, irrevocably, absolutely unreachable. And that 6% is shrinking. With every passing moment, more galaxies slip beyond the cosmic event horizon. Eventually, over the next 100 billion years or so, every galaxy outside our local gravitational neighborhood will have crossed the threshold. The lights will go out, one by one, as galaxy after galaxy accelerates beyond the speed of light relative to us, and its light is redshifted into oblivion. This is not science fiction. This is not speculation. This is the direct, mathematically rigorous, observationally confirmed consequence of the accelerating expansion of the universe. And it is the reason humanity will never escape the Milky Way. But wait, you might say. if 6% of galaxies are still reachable, does that not mean we could at least reach some of them? Could we at least expand beyond the Milky Way to nearby galaxies? The answer involves understanding our cosmic neighborhood in more detail, and this brings us to the concept of the local group. The local group is a collection of approximately 80 galaxies that are gravitationally bound to each other. The dominant members are the Milky Way, the Andromeda galaxy, and the Triangulum galaxy. But the group also includes dozens of smaller dwarf galaxies, many of which orbit the Milky Way or Andromeda as satellites. The local group spans a region about 10 million light-years across. And here's the key point. Because the galaxies in the local group are gravitationally bound, the expansion of the universe does not pull them apart. Gravity within the local group is strong enough to overcome the expansion of space. The galaxies in our local group are held together, orbiting each other, slowly falling toward each other, and in some cases actively colliding. This means that, in principle, the galaxies of the local group are reachable. They are not being carried away by the expansion of the universe. They are close enough and gravitationally connected enough that the expansion of space between them is negligible compared to their mutual gravitational attraction. So, the local group represents the maximum possible extent of humanity's reach. Not just in practice, but in principle. Not just with current technology, but with any technology ever. The local group is our cosmic island, our permanent home. Everything within it is, at least theoretically, accessible. Everything outside it is, or will eventually become, forever unreachable. Now, I want you to pause and really absorb what I have just said, because it is perhaps the single most important conclusion of this entire video. The local group. A collection of approximately 80 galaxies spanning about 10 million light-years represents the absolute upper limit of what humanity, or any civilization based in the Milky Way, can ever hope to reach or interact with. Not because of limited technology, not because of insufficient ambition, not because we haven't tried hard enough, but because the laws of physics, the expansion of the universe and the nature of space-time itself have drawn an invisible, unbreakable boundary around us. Everything within that boundary is our domain, our possible future. Everything outside that boundary is eternally, permanently, unreachably beyond us. And even within the local group, the distances are so enormous, the travel times so vast, that reaching other galaxies within it represents a challenge of almost inconceivable difficulty. Andromeda is 2.5 million light-years away. Even at the speed of light, it would take 2.5 million years to get there. At 10% of the speed of light, it would take 25 million years. These timescales are so far beyond the lifetime of any individual, any civilization, any species, that they are almost meaningless in practical terms. Could we, in principle, send something to Andromeda? Perhaps. In 1 million years with technology we cannot currently imagine. But the key word is in principle. In practice, even the local group is almost certainly beyond our practical reach. And beyond the local group, there is nothing. Only the ever-expanding void. Let us now talk about the collision that is coming, because it is one of the most dramatic events in the future history of our galaxy, and because it illustrates an important point about our cosmic prison. The Milky Way and the Andromeda galaxy are on a collision course. Right now, at this very moment, Andromeda is hurtling toward us at approximately 110 kilometers per second. In roughly 4.5 billion years, the two galaxies will collide. Now, when I say collide, I do not mean that stars will smash into each other. Remember the enormous distances between stars that we discussed earlier? Even within a galaxy, stars are so far apart that when two galaxies merge, the probability of any two stars actually colliding is virtually zero. Instead, what happens is that the gravitational fields of the two galaxies interact, distorting and reshaping the distribution of stars over hundreds of millions of years. Streams of stars are torn from their parent galaxies and flung into intergalactic space. Gas clouds collide and compress, triggering intense bursts of new star formation. The spiral structures of both galaxies are destroyed, and over a period of about 1 to 2 billion years, the two galaxies merge into a single, larger, roughly elliptical galaxy. Astronomers have given this future-merged galaxy various names, including Milkomeda and Milkdromeda. This collision might seem like good news for our escape prospects. After all, if Andromeda is coming to us, we do not need to travel to it. But the collision does not help us escape the local group. It merely rearranges the furniture within our prison. After the merger, we will be in a larger galaxy, but we will still be in the local group. The other galaxies of the local group will still be there, slowly falling inward, and over billions of years, most of them will merge as well, eventually forming one enormous galaxy where the local group used to be. But beyond that merged supergalaxy, the rest of the universe will continue to accelerate away. The collision with Andromeda changes our local environment, but it does nothing to alter the fundamental physics that traps us. We are rearranging deck chairs on the Titanic. If the Titanic were a galaxy and the iceberg were the expansion of the entire universe. And this brings me to what I find to be the most haunting aspect of our cosmic imprisonment, something I touched on earlier but want to explore in much more depth. It is the fate of the observable universe in the far future, and what it means for any civilizations that might exist millions or billions or trillions of years from now. Remember that the expansion of the universe is carrying distant galaxies away from us, and that this expansion is accelerating. As time goes on, more and more galaxies cross beyond the cosmic event horizon and become unreachable. But it is not just that they become unreachable. Eventually, they also become invisible. The light from those galaxies, as it travels through expanding space, is stretched to longer and longer wavelengths. It is redshifted. As the expansion accelerates, the redshift becomes more and more extreme, until the light from distant galaxies is stretched so far that it becomes undetectable. First, it shifts from visible light to infrared, then from infrared to microwave, then from microwave to radio waves so long and so faint that no conceivable instrument could detect them. One by one, the galaxies wink out, not because they have stopped shining, but because their light can no longer reach us. Cosmologists have calculated that in roughly 100 billion years, approximately 7 times the current age of the universe, every galaxy outside the local group will have faded from view. The night sky, from the perspective of our descendants, will contain only the stars of their own galaxy, the merged remnant of the Milky Way, Andromeda, and the other local group members. There will be no other galaxies visible, no other island universes in any direction, just one enormous galaxy floating in an apparently empty void. And here's the truly terrifying part. The evidence for the expansion of the universe will also have disappeared. The cosmic microwave background radiation, the remnant glow from the Big Bang that is one of the strongest pieces of evidence for the expansion of the universe and the Big Bang itself, will have been redshifted to such extreme wavelengths that it will be completely undetectable. The distant supernovae that first revealed the accelerating expansion will no longer be visible. The distribution of galaxies that reveals the large-scale structure of the universe will be gone, replaced by a single isolated galaxy surrounded by nothing. A civilization arising in that far future galaxy, if one does arise, will look at the universe and see a very different picture than the one we see today. They will see a single galaxy, their own, surrounded by infinite darkness. They will have no evidence of the Big Bang. They will have no evidence of the expansion of the universe. They will have no evidence that their galaxy is one of trillions. They will, rationally and scientifically, conclude that their galaxy is the entire universe, a single island of matter floating in a static, eternal void. They will be wrong, but they will have no way of knowing they are wrong. Every piece of evidence that could tell them the truth will have been erased by the very expansion it would have revealed. We are living in a cosmologically privileged era. We exist at a time when the universe is still young enough, still compact enough, still slow enough in its expansion, that we can see the evidence. We can see the other galaxies, we can detect the cosmic microwave background. We can measure the redshifts and calculate the expansion rate, and deduce the Big Bang and infer the existence of dark energy. We can look out at the cosmos and see the truth, that the universe is vast and expanding and accelerating and filled with trillions of galaxies that are slowly slipping beyond our reach. Future civilizations will not have this privilege. They will live in ignorance, not because they are less intelligent, but because the evidence will literally no longer exist. We are the universe's witnesses. We are seeing something that can only be seen now, in this brief cosmological window, and once that window closes, the truth will be lost forever. There is something both beautiful and deeply sad about that. Now, let us talk about the force that is driving this cosmic imprisonment. The invisible warden of our galactic prison, the most mysterious and powerful force in the universe. Dark energy. The story of dark energy begins in 1998, with two teams of astronomers who were trying to measure the rate at which the expansion of the universe was slowing down. You see, at that time, most cosmologists believed that the expansion was decelerating. Gravity, the attractive force between all matter in the universe, should have been pulling everything back together, gradually slowing the expansion that began with the Big Bang. The question was not whether the expansion was slowing, but how fast. Was it slowing enough to eventually stop and reverse, leading to a big crunch where the universe collapses back on itself? Or was it slowing down but never quite stopping, leading to an eternal but ever slower expansion? To answer this question, two teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, set out to measure the distances and recession velocities of distant Type 1a supernovae. Type 1a supernovae are a particular kind of stellar explosion that always reaches approximately the same peak brightness, making them useful as standard candles, objects of known luminosity that can be used to calculate distances. By comparing the observed brightness of distant supernovae to their known luminosity, the teams could determine how far away they were, and by measuring their redshift, they could determine how fast they were receding. What they expected to find was evidence of deceleration. The distant supernovae should have been slightly brighter than expected, indicating that they were slightly closer than expected, indicating that the expansion was slowing down. What they actually found was the opposite. The distant supernovae were dimmer than expected. They were farther away than they should have been. The expansion of the universe was not slowing down at all. It was speeding up. The universe was accelerating. This was, to put it mildly, a shock to the scientific community. It was like throwing a ball in the air, and instead of seeing it slow down and fall back, watching it accelerate upward, faster and faster, with no sign of stopping. Something was pushing the universe apart. Something that acted against gravity. Something that grew stronger as the universe expanded. That something was given the name dark energy. And in 2011, Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics for their discovery. So, what is dark energy? The honest answer is we do not know. Dark energy is one of the deepest unsolved mysteries in all of physics. We know it exists because we can see its effects. We know it makes up approximately 68% of the total energy content of the universe. We know it acts as a repulsive force on cosmological scales, pushing galaxies apart and accelerating the expansion of the universe. But we do not know what it is. We do not know why it exists. We do not know whether it is a property of space itself, or a new kind of energy field, or something else entirely. There are several theoretical candidates for dark energy. The simplest and most widely accepted is the cosmological constant, usually denoted by the Greek letter lambda. The cosmological constant was originally introduced by Einstein himself in 1917. Not because he thought the universe was accelerating, but because he wanted his equations of general relativity to permit a static universe, one that was neither expanding nor contracting. When Hubble discovered that the universe was expanding, Einstein reportedly called the cosmological constant his biggest blunder and abandoned it. But decades later, the discovery of accelerating expansion brought it roaring back. The cosmological constant can be interpreted as the energy density of empty space, the vacuum energy. According to quantum field theory, even completely empty space is not truly empty. It is filled with fleeting, ephemeral quantum fluctuations, virtual particles popping in and out of existence on timescales so short that they cannot be directly observed. These fluctuations contribute energy to the vacuum, and that energy, according to general relativity, has gravitational effects. If the vacuum energy is positive, it acts as a repulsive force, pushing space apart. This is exactly the kind of behavior we observe in dark energy. But there is a problem, and it is a big one. When physicists try to calculate the vacuum energy from first principles using quantum field theory, they get a number that is absolutely enormous, roughly 10 to the power of 120 times larger than the observed value of dark energy. Let me say that again. The theoretical prediction for the vacuum energy is off by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. This is sometimes called the worst prediction in the history of physics, and it is not an exaggeration. There is no known explanation for why the actual value of dark energy is so incredibly, absurdly small compared to the theoretical prediction. This discrepancy is known as the cosmological constant problem, and it remains one of the most significant unsolved problems in all of physics. Other theoretical candidates for dark energy include quintessence, a hypothetical dynamic energy field that changes over time, and modifications to general relativity that alter the behavior of gravity on cosmological scales. But none of these alternatives have been confirmed by observation, and the cosmological constant remains the simplest and most consistent explanation for the data. Regardless of what dark energy actually is, its effect on our cosmic prison is clear and devastating. Dark energy is pushing the universe apart. It is accelerating the expansion. And because dark energy is a property of space itself, as space expands, more dark energy is created, which causes space to expand even faster, which creates even more dark energy, in a runaway feedback loop that will continue forever. Dark energy does not deplete. It does not run out. It does not weaken. As the universe grows, there is simply more of it. And with every passing moment, the distances between galaxy clusters grow a little faster, and the cosmic event horizon shrinks a little more, and our prison becomes a little tighter. There is one more thing about dark energy that deserves discussion, and that is what happens if dark energy is not a constant. If dark energy is truly a cosmological constant, then its energy density remains the same as the universe expands, and the expansion accelerates at a steady, predictable rate. This leads to the Big Freeze scenario, in which the universe expands forever. Galaxies drift apart, stars burn out, and the universe slowly dies a cold, dark, quiet death over trillions of years. This is the most widely accepted model for the ultimate fate of the universe, but there is another possibility. If dark energy is not a constant, if it is some kind of dynamic field whose strength increases over time, then the expansion of the universe could accelerate without bound, eventually becoming so fast that it overcomes all forces, even gravity, even the electromagnetic force, even the nuclear forces that hold atoms together. In this scenario, called the Big Rip, the expansion of space would first tear apart galaxy clusters, then galaxies, then solar systems, then planets, then atoms, then the fabric of space-time itself. Everything in the universe would be ripped apart, down to the subatomic level, in a final, catastrophic explosion of expansion. Current observations suggest that this scenario is unlikely, that dark energy really is close to a cosmological constant and is not increasing in strength. But we cannot rule it out entirely. The nature of dark energy is still too poorly understood for us to be completely certain of the universe's ultimate fate. Whether the universe ends in a big freeze or a big rip, the conclusion for humanity is the same. Dark energy is the warden of our cosmic prison, and it is not going anywhere. It will continue to push the universe apart, continue to accelerate the expansion, continue to carry galaxies beyond our reach for as long as the universe exists. And there is nothing we can do about it. Nothing any civilization can do about it. Dark energy operates on the scale of the cosmos, and no local action, no technology, no amount of energy can counteract it. It is like trying to bail out the ocean with a teaspoon. The scale of the force we are fighting is so vastly beyond our capabilities that the comparison itself breaks down. Now, I want to take you on a journey into the far future, because understanding what happens to the universe over the next trillions and trillions of years drives home the permanence of our imprisonment in a way that nothing else can. Let us start a cosmic clock and watch the universe evolve. Right now, we live in what cosmologists call the stelliferous era, the age of stars. This is the period in which stars are born, live out their nuclear lives, and die. It began roughly 100 million years after the Big Bang, when the first stars ignited, and it will continue for perhaps another 100 trillion years, until the last star burns out. During this era, the universe is luminous. Stars shine, galaxies glow, planets are warmed. Life, at least in our case, exists. We are in the golden age of the universe, the brief, bright interval during which the cosmos is filled with light and energy and the potential for complexity and consciousness. But the stelliferous era is just a tiny fraction of the universe's total lifespan. If you were to compare the entire future history of the universe to a human lifetime, the stelliferous era would not even be the first breath of a newborn baby. It would be more like a single quantum fluctuation in the first nanosecond of existence. The overwhelming majority of the universe's future lies in darkness. Let us fast forward. In about 4.5 billion years, as I mentioned earlier, the Milky Way and Andromeda will collide and merge. The Sun will also be nearing the end of its life around this time. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core, swell into a red giant star, engulf the inner planets, possibly including Earth, and eventually shed its outer layers, leaving behind a dense, hot remnant called a white dwarf. The Earth, if it is not consumed by the expanding Sun, will be scorched and sterilized. Its oceans long since boiled away, its atmosphere long since stripped. Whether humanity still exists at this point is anyone's guess. If we have survived, we will have long since left Earth. But we will still be in the Milky Way, or rather, in the merged Milky galaxy, and we will still be trapped. In about 100 billion years, all galaxies outside the local group will have receded beyond the observable universe. The night sky will go dark, except for the stars of our own merged supergalaxy. The cosmic microwave background will have faded below detectability. The universe, from our perspective, will appear to contain nothing but our own galaxy floating in an infinite void. In about 100 trillion years, the last stars will burn out. Star formation will have ceased long before this, as the gas clouds from which stars form are gradually consumed or ejected from galaxies. The last generation of stars will be red dwarfs, the smallest and most frugal of all stars, which burn their hydrogen fuel so slowly that they can shine for trillions of years. But even they must eventually exhaust their fuel. When the last red dwarf flickers and dies, the stelliferous era will end. The universe will enter a new phase, one of increasing darkness and cold. The only light will come from the feeble glow of white dwarfs slowly cooling to become black dwarfs, from occasional flashes as neutron stars collide, from the rare gravitational interactions that fling objects into trajectories that cause brief bursts of friction and heat. But these sources of light are rare and dim, mere candle flames in a universe-sized cave. After the last stars die, the universe enters what is sometimes called the degenerate era. In this era, the dominant objects in the universe are stellar remnants: white dwarfs, neutron stars, and black holes. White dwarfs are the remnants of small to medium-sized stars like our Sun. They are about the size of the Earth, but with the mass of the Sun, incredibly dense objects that slowly radiate away their residual heat over trillions of years. Neutron stars are the remnants of more massive stars, even denser than white dwarfs, with masses 1 to 2 times that of the Sun compressed into a sphere about 20 kilometers across. And black holes are the remnants of the most massive stars, objects so dense that not even light can escape their gravitational pull. During the degenerate era, these remnants drift through the darkness of an expanding, cooling universe. Occasionally, 2 remnants pass close enough to interact gravitationally, perhaps flinging one into a new trajectory or forming a binary system. But these interactions become rarer and rarer as the universe expands and the distances between objects grow. There is a speculative possibility that matter itself may not be permanent. According to some theories in particle physics, protons, the particles that make up the nuclei of atoms, may eventually decay. Proton decay has never been observed, and its existence is not certain. But several grand unified theories predict that protons have a half-life of approximately 10 to the power of 36 years. If this is true, then on timescales of 10 to the power of 40 years or so, all ordinary matter, every atom, every molecule, every structure made of baryonic matter, will have dissolved into radiation and lighter particles. White dwarfs will evaporate. Neutron stars will dissolve. Planets and asteroids and dust, everything made of atoms, will simply cease to exist. Only black holes will remain. If proton decay does not occur, then matter persists, but in an increasingly cold and inert state. White dwarfs cool to absolute zero. Neutron stars cool to absolute zero. Everything becomes frozen, dark, inert, and dead. Either way, the universe becomes a very empty, very dark, very cold place. Even black holes, the most extreme and durable objects in the universe, are not permanent. In 1974, Stephen Hawking made a revolutionary theoretical discovery. Black holes emit radiation. This radiation, now called Hawking radiation, is a quantum mechanical effect that occurs at the event horizon of a black hole. Very roughly, quantum fluctuations near the event horizon can cause pairs of virtual particles to separate, with one falling into the black hole and the other escaping into space. The escaping particle carries away a tiny amount of the black hole's energy, causing the black hole to lose mass very slowly. Over immense timescales, a black hole will lose all of its mass through Hawking radiation and evaporate completely. For a stellar mass black hole, this process takes about 10 to the power of 67 years. For a supermassive black hole, the kind that sits at the center of galaxies and has a mass of millions or billions of times the Sun's mass, the evaporation time is on the order of 10 to the power of 100 years, a googol years. A googol is a 1 followed by 100 zeros. This is an amount of time so vast that it dwarfs the current age of the universe the way the current age of the universe dwarfs the time it takes a photon to cross a proton. And yet, even this unfathomable span of time eventually passes. And when the last black hole evaporates, when the last bit of matter and energy is converted into a bath of increasingly cold, increasingly sparse, increasingly redshifted photons, the universe enters its final state, heat death. Heat death is the ultimate consequence of the second law of thermodynamics, which states that the entropy of a closed system always increases over time. Entropy, roughly speaking, is a measure of disorder, of how spread out and evenly distributed energy is. The second law says that energy always flows from concentrated to dispersed, from hot to cold, from ordered to disordered. Stars are sources of concentrated energy. When they shine, they are converting concentrated nuclear energy into dispersed thermal radiation, increasing the entropy of the universe. Black holes, when they form and when they evaporate, increase the entropy of the universe. Every physical process increases entropy, slowly moving the universe toward its maximum entropy state. The heat death of the universe is the state of maximum entropy. In this state, all energy is perfectly evenly distributed. There are no temperature differences, no energy gradients, no concentrations of matter or energy that could be used to do work, no processes that can extract useful energy from the environment, no computation, no thought, no life. Just an infinite, uniform, cold, dark expanse of space, expanding forever, with nothing happening, nothing changing, nothing existing in any meaningful sense. The temperature of the universe approaches, but never quite reaches, absolute zero. Photons stretch to wavelengths larger than the observable universe, and time, in any practical sense, ceases to have meaning. There are no events to mark its passage. There are no observers to experience it. There is only the eternal, unchanging, silent void. This is the ultimate fate of our cosmic prison. The Milky Way, or whatever merged galaxy it eventually becomes, will not exist forever. Its stars will die, its matter will decay, its black holes will evaporate, and in the end, the prison itself will dissolve, leaving nothing but the infinite, expanding, empty void. There will be nothing left to escape from, and no one left to escape. There is one more concept from the far future that I want to mention, because it is both fascinating and deeply unsettling. It is the concept of the Boltzmann brain. In a universe that exists for an infinite amount of time in a state of heat death, quantum fluctuations continue to occur. These fluctuations are incredibly unlikely to produce anything macroscopic, but given infinite time, even the most improbable events must eventually occur. This includes the spontaneous assembly, through random quantum fluctuations, of a conscious observer. A brain, complete with memories and thoughts and sensory experiences, could pop into existence for a brief moment before dissolving back into the void. This is called a Boltzmann brain, named after the 19th century physicist Ludwig Boltzmann, who first considered related ideas about thermodynamic fluctuations. The troubling thing about Boltzmann brains is that in some models of the universe, they are predicted to be far more common than real observers. Observers who evolved through biological processes over billions of years in a normal, star-filled universe. If this is true, then a randomly selected conscious observer in the universe is overwhelmingly more likely to be a Boltzmann brain, a fluctuation that appears briefly in the void with false memories of a non-existent past, than a real person living on a real planet. This raises deeply uncomfortable philosophical questions about the nature of reality and consciousness. Are we Boltzmann brains? Probably not, because Boltzmann brains would have random, incoherent experiences, whereas our experiences are remarkably consistent and orderly. But the mere fact that the question can be seriously asked tells us something about how strange and vast and mind-bending the far future of the universe truly is. Let me bring us back from the far future and return to the question at the heart of this video. We have now seen why humanity is trapped in the Milky Way from the perspectives of scale, the speed of light, the expansion of the universe, dark energy, the local group, and the far future. We have established that the barriers to escape are not technological, but physical, rooted in the fundamental laws of nature. But there is one more thing we need to do before we can fully answer our question. We need to examine every conceivable escape route that science has ever proposed and understand why each one fails. Because you might be thinking, surely there must be some way out. Surely, with enough ingenuity, enough time, enough technological advancement, we can find a loophole in the laws of physics. So, let us go through them, one by one, and see. The first and most famous theoretical escape route is the Alcubierre warp drive. In 1994, the Mexican physicist Miguel Alcubierre published a paper in the journal Classical and Quantum Gravity that proposed a startling idea, a way to travel faster than light without violating general relativity. Alcubierre's concept is elegant. Instead of trying to accelerate a spaceship to superluminal velocities through space, which is impossible, you would instead create a warp bubble around the spaceship by distorting space-time itself. Space in front of the bubble would be contracted, bringing the destination closer, while space behind the bubble would be expanded, pushing the origin further away. The spaceship inside the bubble would be stationary relative to its local space. It would not be moving through space at all. It would be the space around it that would be moving, carrying the bubble and everything inside it along at effectively superluminal speeds. Since the ship is not moving through space, only space is moving around the ship. This does not violate special relativity's prohibition on faster-than-light travel. If this sounds too good to be true, that is because, in its current form, it is. The Alcubierre warp drive has several devastating problems that may well be insurmountable. The first and most serious is that it requires what physicists call exotic matter, matter with negative energy density. In ordinary physics, all matter and energy have positive energy density. Negative energy density is a strange and exotic property that has only been observed in extremely limited and tiny quantum effects, such as the Casimir effect, where two closely spaced metal plates experience a tiny attractive force due to the exclusion of certain quantum fluctuations between them. The Casimir effect involves incredibly tiny amounts of negative energy, far less than what would be needed for a warp bubble. Alcubierre's original calculations showed that the warp drive would require a quantity of negative energy equivalent to the mass energy of the planet Jupiter. Later, work by Harold White and others has reduced this estimate somewhat, but the required amount of negative energy is still enormous, and we have no idea how to produce it, or even whether it can be produced in the quantities needed. The second problem with the Alcubierre drive is the energy requirement, even if negative energy could be produced. The total energy needed to create and sustain a warp bubble is staggering, potentially exceeding the total energy output of the Sun over its entire lifetime. For a single trip. The third problem is that the interior of the warp bubble would be causally disconnected from the exterior. The pilot inside the bubble would have no way to steer, accelerate, decelerate, or control the bubble in any way, because signals cannot cross the boundary of the bubble from inside to outside. You would essentially create the bubble, set its destination, and then be a helpless passenger inside it, unable to change course or stop. The fourth problem is that, according to some analyses, the front edge of the warp bubble would accumulate an enormous amount of high-energy radiation, which would be released in a devastating blast at the destination when the bubble is deactivated. You would arrive at your destination and immediately annihilate it with a burst of gamma rays. More recent work by Eric Lentz in 2021 has proposed warp drive solutions that do not require negative energy, using positive energy configurations to achieve similar effects. But these proposals remain highly speculative, have not been experimentally verified, and still face enormous theoretical and practical challenges. As of our current understanding of physics, the Alcubierre warp drive remains a mathematical curiosity rather than a practical possibility. And even if, through some miracle of future physics, we could build a working warp drive, there is a deeper question. Could it actually save us from cosmic imprisonment? The answer is, probably not for most of the universe. A warp drive could potentially allow faster-than-light travel to nearby galaxies, those still within or near the cosmic event horizon. But for the vast majority of the universe, the galaxies that are already receding faster than light, a warp drive would need to outrun the expansion of space itself. And while a warp drive can in principle achieve any speed by contracting enough space in front and expanding enough space behind, the amount of space that needs to be contracted and expanded grows without bound as you try to reach more distant, more rapidly receding galaxies. The energy requirements would grow accordingly, eventually exceeding any conceivable energy source. The warp drive does not solve the fundamental problem. It might push the boundary of our reachable universe outward somewhat, but it cannot eliminate the cosmic event horizon. The expansion of the universe is not a barrier you can break through with a clever enough engine. It is a feature of space-time itself, and no amount of warping or distortion can change the global expansion rate of the universe. The second theoretical escape route is the wormhole, also known as an Einstein-Rosen bridge. Wormholes are solutions to the equations of general relativity that describe a tunnel through space-time connecting two distant points. If you could enter one end of a wormhole and exit the other, you could travel vast distances almost instantaneously, bypassing the need to traverse the intervening space. Wormholes were first described mathematically by Albert Einstein and Nathan Rosen in 1935, which is why they are sometimes called Einstein-Rosen bridges. The concept has been popularized by science fiction, most notably in films like Interstellar and television shows like Star Trek. The theoretical basis for wormholes is solid in the sense that they are valid solutions to Einstein's field equations. They are not forbidden by general relativity. However, the devil is in the details. The original Einstein-Rosen bridge is not traversable. It connects two black holes, and any object that enters one end would be destroyed by the singularity inside the black hole long before it could emerge from the other end. In 1988, Kip Thorne and his student Michael Morris showed that traversable wormholes that a person could actually travel through and survive, are theoretically possible, but only if they are held open by exotic matter with negative energy density. We have encountered this requirement before with the Alcubierre drive, and the same problems apply. We do not know how to produce exotic matter in the quantities needed, and we do not know whether it is even possible to do so. Beyond the exotic matter problem, wormholes face numerous other challenges. We do not know how to create a wormhole. There is no known physical process that produces wormholes, and the energy required to create one, if it is even possible, would be enormous. We do not know how to stabilize a wormhole once created. Even if exotic matter could hold a wormhole open, any perturbation, any passing particle or quantum fluctuation might cause it to collapse. We do not know how to control the destination of a wormhole. Even if we could create a stable, traversable wormhole, we would need some way to connect one end to a specific distant location, which requires either moving one end of the wormhole to that location, which brings us back to the problem of traversing vast distances, or somehow creating a wormhole with one end already at the destination, which we have no idea how to do. And we do not know whether large-scale wormholes are even possible. Some physicists believe that the quantum gravity effects that operate at the Planck scale might prevent wormholes from existing at macroscopic scales. In quantum gravity, which combines the principles of quantum mechanics with general relativity, space-time may be foamy at incredibly tiny scales, with wormholes opening and closing constantly. But these quantum wormholes would be unimaginably small, perhaps 10 to the power of minus 35 meters across, far too small for anything macroscopic to pass through. Enlarging such a wormhole to human scale, if it is even possible, might require energy on the order of the Planck energy, approximately 10 to the power of 19 giga-electronvolts, which is far beyond our reach. The verdict on wormholes is similar to the verdict on warp drives. They are fascinating theoretical possibilities, but they face enormous, possibly insurmountable obstacles. And even if they could be built, they would not necessarily solve the problem of cosmic imprisonment. A wormhole connects two specific points in space-time. To escape the Milky Way and reach distant galaxies, you would need to somehow create a wormhole with one end here and the other end at your destination. But if your destination is beyond the cosmic event horizon, already receding faster than light, it is not clear that a wormhole could maintain a connection to such a point. The expansion of space might tear the wormhole apart, or the causal disconnection between the 2 points might prevent the wormhole from forming in the first place. These are open questions in theoretical physics, and there are no definitive answers. But the obstacles are so severe that wormholes, like warp drives, remain firmly in the realm of science fiction rather than practical escape routes. The third approach to escaping the Milky Way involves not exotic physics, but rather brute force engineering. Generation ships. A generation ship is exactly what it sounds like. A massive spacecraft designed to support a self-sustaining human population for the entire duration of an interstellar or intergalactic journey. Since the journey would take far longer than any individual human lifespan, multiple generations would be born, live and die aboard the ship, with each generation passing on the mission to the next. Generation ships have been a staple of science fiction for nearly a century, and the concept is at least physically possible in the sense that it does not require any new physics. You build a very large ship, put a lot of people on it, include everything they need to survive and reproduce, point it at a distant destination, and launch. The physics of the journey is straightforward: Newton's laws, orbital mechanics, rocket propulsion. The challenges are in the engineering and the biology and the sociology. Let us consider the challenges of a generation ship to Andromeda. At 10% of the speed of light, a speed that is extremely optimistic given current technology, but perhaps achievable with advanced propulsion like nuclear pulse engines or fusion drives, the journey would take approximately 25 million years. 25 million years of continuous travel in a sealed, self-sustaining habitat, with generations of humans being born and dying en route. The engineering challenges alone are staggering. No structure built by humans has ever lasted more than a few thousand years. The oldest surviving buildings are perhaps 5,000 or 6,000 years old, and they have required constant maintenance and repair. A generation ship would need to function perfectly for 25 million years with no external support, no resupply, no rescue. Every system would need to be either perfectly reliable for millions of years, an impossibility for any physical device, or completely repairable using only the resources available aboard the ship. The ship would need to protect its inhabitants from cosmic radiation, micrometeorites, and the vacuum of intergalactic space for the entire journey. It would need to recycle every atom of air, water, and food with essentially perfect efficiency. Any waste, any loss, any gradual degradation of the recycling systems would be fatal over millions of years. The biological challenges are equally daunting. A viable human population aboard a generation ship would need to be large enough to avoid genetic bottlenecks, the loss of genetic diversity that occurs in small, isolated populations and can lead to inbreeding, increased susceptibility to disease, and reduced adaptability. Estimates vary, but maintaining a genetically healthy population for millions of years would likely require thousands or tens of thousands of individuals. This means the ship would need to be enormous, a small city or even a small nation floating through space. Over 25 million years, evolution would take its course. Humans would evolve, potentially diverging significantly from the humans who originally boarded the ship. Mutations would accumulate. Natural selection, operating in the unique environment of the ship, would shape the population in unpredictable ways. After millions of years, the beings who arrive at Andromeda might be as different from us as we are from our ape-like ancestors who lived 25 million years ago. They would be a new species. They would not be human in any meaningful sense. The sociological challenges are perhaps the most insurmountable of all. Human societies are inherently unstable. Over the course of just a few thousand years of recorded history, we have seen the rise and fall of countless civilizations, empires, and cultures. Wars, revolutions, famines, plagues, social collapse, these are recurring features of human history. A generation ship would need to maintain a stable, functional society for 25 million years, a span of time so far beyond anything in human experience that it is impossible to predict what would happen. Would the inhabitants remember their mission? Would they maintain the technology needed to operate and navigate the ship? Would they develop new religions or ideologies that reject the mission? Would they wage wars? Would they fragment into rival factions? Would they forget that they are on a ship at all, coming to believe that the ship is the entire world? Language itself would change beyond recognition. After 25 million years, the language spoken by the ship's inhabitants would bear no resemblance to any language spoken today. Cultural drift would be total. The original mission, the original reason for the journey, would be lost in the mists of an inconceivably deep past. And all of this assumes that the ship survives for 25 million years, which it almost certainly would not. Over such timescales, even the most robust materials degrade. Metals corrode. Radiation damages electronics and structural materials. Micrometeorite impacts accumulate. The probability of a catastrophic failure, a hull breach, a radiation event, a system's collapse, over 25 million years is effectively 100%. The generation ship approach fails not because of any single insurmountable obstacle, but because the timescales involved are so far beyond anything that human engineering, biology, or society can cope with that the very concept becomes meaningless. The fourth approach involves cryogenic preservation, the idea of freezing humans for the duration of the journey and thawing them at the destination. This eliminates the sociological problems of the generation ship approach, because the passengers are unconscious and unchanging for the duration of the trip. But it introduces its own severe problems. Current cryogenic technology cannot preserve a living human being. When cells are frozen, water inside them forms ice crystals that tear apart cell membranes and destroy delicate cellular structures. A technique called vitrification, which replaces the water in cells with a glass-like antifreeze solution, can prevent ice crystal formation, but it has only been successfully applied to small organisms and individual organs. Preserving an entire human body in a state from which it could be revived is currently beyond our technology, and may remain so for a long time. And even if we could perfectly preserve a human being for the duration of the journey, we would still need a ship capable of maintaining that preservation for millions of years. The cryogenic systems would need to be powered, monitored, and maintained for the entire trip. Any failure, any interruption in power, any malfunction in the preservation systems would be fatal. And as we discussed, maintaining any technological system for millions of years is effectively impossible. The fifth approach is perhaps the most creative: digital consciousness, or mind uploading. The idea is to scan the complete structure of a human brain, down to the level of individual neurons and synapses, and create a digital copy that can run on a computer. This digital mind would have all the memories, personality, and consciousness of the original person, but would exist as software rather than biology. A digital mind could be transmitted as a beam of electromagnetic radiation, traveling at the speed of light to a distant destination. Or it could be loaded onto a small, lightweight computer aboard a tiny spacecraft, requiring far less energy to accelerate than a massive generation ship. The appeal of mind uploading for interstellar or intergalactic travel is obvious. A digital mind does not need food, water, or air. It does not age. It does not suffer from the psychological problems of long confinement. It can be copied, backed up, and repaired. And it can be transmitted at the speed of light, the fastest possible speed. But mind uploading faces its own daunting challenges. First, we do not currently know how to scan a brain at the necessary resolution. The human brain contains approximately 86 billion neurons, each connected to thousands of other neurons via synapses, for a total of roughly 100 trillion synaptic connections. The precise arrangement of these connections, as well as the chemical properties of each synapse, would need to be captured perfectly. We are nowhere near being able to do this. Second, we do not know whether a digital copy of a brain would actually be conscious. This is the hard problem of consciousness, one of the deepest unsolved problems in philosophy and neuroscience. Is consciousness a product of the specific physical substrate of the brain, the wet, biological neurons firing electrochemical signals? Or is it a product of the abstract pattern of information processing, regardless of the substrate? If the former, then a digital copy would be a philosophical zombie, processing information without any subjective experience. If the latter, then the digital copy would be conscious. We do not know the answer. Third, even if mind uploading works and produces genuine consciousness, there is the ship of Theseus problem. Is the uploaded mind really you? Or is it a copy, a new person with your memories, while the original you remains behind or is destroyed in the scanning process? If it is a copy, then mind uploading does not save you. It creates a new being that thinks it is you but is not. This is not a practical problem, but a deep philosophical one, and it matters enormously for the question of whether mind uploading represents a genuine escape from the Milky Way, or merely the creation of copies that think they have escaped. And even if all of these problems could be solved, mind uploading still faces the ultimate barrier: the speed of light. A digital mind transmitted as a radio signal or a laser beam still travels at the speed of light. And the speed of light, as we have discussed, is not fast enough to outrun the expansion of the universe. A digital mind beamed toward a galaxy beyond the cosmic event horizon would never arrive. The signal would be redshifted into oblivion, stretched by the expansion of space until it was undetectable and unintelligible. Mind uploading might help with travel within the Milky Way or even within the local group, but it cannot solve the fundamental problem of cosmic imprisonment. We are still trapped by the speed of light and the expansion of space. The sixth approach is the concept of von Neumann probes, named after the mathematician John von Neumann, who first described the concept of self-replicating machines. A von Neumann probe is a spacecraft that, upon arriving at a new star system, uses local resources, asteroids, moons, planetary materials, to build copies of itself. These copies then travel to neighboring star systems and repeat the process. The result is an exponentially expanding wave of probes that spreads across the galaxy and eventually to other galaxies without requiring the original launching civilization to invest the energy needed to send probes to every destination individually. The mathematics of von Neumann probes are compelling. Even at relatively modest speeds, say 10% of the speed of light, and even with significant replication times, say 1,000 years per generation, a wave of von Neumann probes could spread across the entire Milky Way in 10 to 50 million years. That is a long time by human standards, but it is a tiny fraction of the age of the galaxy. In principle, von Neumann probes could even be sent to other galaxies in the local group, though the travel times would be much longer. But von Neumann probes, like every other approach we have considered, cannot overcome the expansion of the universe. Probes sent toward galaxies beyond the local group face the same problem as any other traveling object. The expansion of space is carrying those galaxies away faster than the probes can approach them. The wave of replication, no matter how fast, is still limited by the speed at which the probes can travel, which is limited by the speed of light, and the speed of light is not fast enough. The von Neumann probe approach might allow us to explore and colonize the Milky Way and perhaps other galaxies in the local group, which is an astonishing achievement by any measure. But it cannot break us out of our cosmic prison. The walls of the prison are not made of distance. They are made of expanding space. And expanding space cannot be crossed by any physical object, no matter how cleverly designed. The seventh and most speculative approach involves directly manipulating the fundamental forces and fabric of the universe. Could a sufficiently advanced civilization learn to control dark energy? Could they counteract the expansion of space locally, creating a region of non-expanding or even contracting space that would serve as a corridor to distant galaxies? Could they alter the properties of space-time itself, changing the rules of the game rather than trying to win within the existing rules? These ideas are not even really science at this point. They are science fiction, or perhaps science fantasy. We have absolutely no understanding of how dark energy could be manipulated. We do not know what dark energy is. We do not know what causes the expansion of space. We do not know how space-time is structured at the most fundamental level. Our best theories, general relativity and quantum field theory, are incomplete and mutually inconsistent in important ways. We need a theory of quantum gravity, a theory that unifies general relativity and quantum mechanics to even begin to address these questions. And we do not have one. String theory, loop quantum gravity, and other candidates for a theory of quantum gravity are mathematically fascinating but experimentally unverified. They might be correct, they might be completely wrong, they might be partially right in ways we do not yet understand. And even if we did have a complete theory of quantum gravity, there is no guarantee that it would reveal a way to manipulate space-time in the ways we would need to escape our cosmic prison. It might instead confirm that the prison is inescapable. The laws of physics might simply not allow the kind of manipulation we would need. Arthur C. Clarke, the great science fiction writer, once said that any sufficiently advanced technology is indistinguishable from magic. This is true, and it is tempting to believe that a civilization, millions or billions of years more advanced than us, would have capabilities that we cannot even imagine, capabilities that might seem like magic to us and might include the ability to escape the cosmic prison. But there is an important distinction between technology that seems magical to a less advanced observer and technology that actually violates the laws of physics. The former is common in human history. Fire seemed magical to those who did not understand combustion. Flight seemed magical to those who did not understand aerodynamics. Nuclear energy seemed magical to those who did not understand atomic physics. But none of these technologies violated any fundamental law. They merely exploited laws that were not yet understood. Escaping the cosmic prison, on the other hand, appears to require violating fundamental laws, or at least exploiting loopholes in those laws that may not exist. The expansion of the universe is not a technological barrier to be overcome. It is a property of space-time itself. And while our understanding of space-time is incomplete, there is no known theoretical framework that suggests a way to counteract the expansion of space over cosmological distances. We are not just pushing against a wall, we are inside the wall. We are made of the same space-time that is expanding, and there may be no way to step outside of it. Now, I promised you that we would also consider the alien perspective, and I think it is one of the most fascinating aspects of this entire topic. Because if humanity is trapped in the Milky Way, then every other civilization in the universe, assuming they exist, is also trapped in their own galaxy or local group. The same physics that imprisons us imprisons everyone. The speed of light is the same everywhere. The expansion of the universe is the same everywhere. Dark energy is the same everywhere. There are no special locations in the universe where the rules are different. No privileged galaxies where the expansion does not apply. This has profound implications for the Fermi paradox, the famous question asked by physicist Enrico Fermi in 1950. If the universe is so vast and so old, and if the conditions for life are not unique to Earth, then where is everybody? Where are the alien civilizations? Why have we not detected their signals, seen their megastructures, or been visited by their probes? There are many proposed solutions to the Fermi paradox, from the Great Filter hypothesis, which suggests that some insurmountable obstacle prevents civilizations from becoming sufficiently advanced, to the zoo hypothesis, which suggests that advanced civilizations are deliberately avoiding contact with us, to the dark forest theory, which suggests that civilizations remain hidden because revealing yourself to the cosmos is dangerous. But the cosmic prison provides another, perhaps simpler answer. Nobody visits anybody because nobody can. The distances between galaxies are too vast, the expansion of the universe is too fast, and the laws of physics are too strict. Even within a single galaxy, the distances between stars are enormous. Even a civilization that has existed for millions of years and has colonized its entire galaxy would still be trapped within it, unable to reach other galaxies. And if those other galaxies are the homes of other trapped civilizations, then the universe might be teeming with intelligent life, each civilization trapped on its own galactic island, each one looking up at the same sky and asking the same question: where is everybody? This is, to me, one of the most profound and melancholy ideas in all of cosmology. The universe might be full of life. There might be billions of civilizations out there, some vastly more advanced than us, some contemplating questions we cannot even formulate. But each one is alone. Each one is sealed inside its own local group, its own cosmic island, separated from every other civilization by the expanding void of space. They might know, as we know, that they are trapped. They might see, as we see, the light of distant galaxies slowly fading away. They might feel, as we feel, the mixture of wonder and sorrow that comes from understanding the vastness and loneliness of the cosmos. Or they might have arisen so far in the future that they see nothing at all, living in a universe that appears to contain only their own galaxy, with no evidence that anything else exists. Either way, they are as trapped as we are. The universe does not care how intelligent you are, how advanced your technology is, how deep your understanding of physics goes. It has built the same prison for everyone. There is a related question that I want to explore, which is whether communication, even if travel is impossible, might be feasible across cosmic distances. Could we at least send signals to civilizations in other galaxies, even if we can never visit them? In principle, electromagnetic signals, radio waves, light, X-rays, travel at the speed of light, which is the fastest speed at which information can be transmitted. A signal sent today to Andromeda would arrive in 2.5 million years. A civilization in Andromeda that detected the signal and replied would send a response that would arrive back here in another 2.5 million years. A round trip of 5 million years. That is a very slow conversation, but it is at least a conversation. You could, in principle, exchange information with another civilization in the local group, albeit over timescales that are meaningless for any individual, but might be meaningful for a civilization or a species. But for galaxies outside the local group, even this slow conversation becomes impossible. Signals sent to galaxies beyond the cosmic event horizon will never arrive. And for galaxies that are currently within the cosmic event horizon but receding rapidly, signals sent today might arrive, but the response might not make it back, because by the time the response is sent, the expansion of space may have carried us beyond the responder's cosmic event horizon. The window for communication is closing, just as the window for observation is closing. Every day that passes, the number of galaxies with which we could exchange even a single signal decreases. In 100 billion years, the only galaxies we can communicate with will be those in our local group, and even then, only if they still exist as separate entities and have not merged into a single galaxy. Communication across the cosmos is, like travel across the cosmos, a prisoner's dream. Theoretically possible in a narrow and shrinking window, practically impossible for almost all destinations. Now, here is something interesting and somewhat counterintuitive that is worth mentioning. You might think that the search for extraterrestrial intelligence, SETI, is pointless if every civilization is trapped in its own galaxy. But that is not quite right. The Milky Way itself contains hundreds of billions of stars, many of which have planetary systems. The number of potentially habitable planets in our galaxy alone is estimated to be in the billions. If there are other civilizations in the Milky Way, they are not separated from us by the expansion of the universe. They are within our galaxy, separated by only tens of thousands of light years at most. The expansion of space within the Milky Way is negligible, completely overwhelmed by the galaxy's own gravity. Civilizations within the Milky Way could, in principle, communicate with each other and even visit each other, given enough time and technology. The cosmic prison traps us in the Milky Way, but it does not isolate us within the Milky Way. If there is other intelligent life in our galaxy, and there might be, then we are not alone. We share our prison with potential neighbors, potential friends, potential correspondents. The universe beyond the Milky Way may be forever out of reach, but the Milky Way itself is a vast and potentially richly populated domain, and exploring it, communicating across it, and perhaps one day colonizing it, is a goal that is not in conflict with the laws of physics. It is the cosmos beyond our galaxy that is close to us, not our galaxy itself. Let me now engage with a question that some of you might have been thinking about throughout this video. You might be thinking, okay, everything you have said is based on our current understanding of physics. But our understanding of physics is incomplete. We do not have a theory of quantum gravity. We do not understand dark energy. There might be fundamental aspects of the universe that we have not yet discovered. Could those unknown aspects provide a loophole, a way out of the cosmic prison? This is a fair question, and it deserves a thoughtful answer. The honest answer is, we do not know. It is possible that future discoveries in physics will reveal new phenomena or new principles that could change our assessment of the situation. History is full of examples of impossible things becoming possible as our understanding of nature deepened. People once thought heavier-than-air flight was impossible. People once thought that the atom was indivisible. People once thought that the sound barrier could not be broken. In each case, new understanding revealed that the supposed impossibility was not fundamental, but was rather a limitation of the prevailing understanding. Could the cosmic speed limit be similarly overturned? Could there be a way to travel faster than light, or to circumvent the expansion of space that we simply have not yet discovered? In principle, anything is possible. Our knowledge of physics is not complete, and there is always room for surprise. But there are important reasons to believe that the barriers we have discussed are more fundamental than the barriers that were previously overturned. The prohibition against heavier-than-air flight was based on incomplete understanding of aerodynamics. It was not derived from any fundamental physical law. The indivisibility of the atom was a hypothesis, not a theorem. The speed of light limit, by contrast, is derived from the most fundamental and well-tested theory in all of physics, Einstein's theories of relativity. Special and general relativity have been tested with extraordinary precision over more than a century. Every prediction they have made has been confirmed. The speed of light limit has been probed from every conceivable angle, and it has held firm. The expansion of the universe has been observed, measured, and confirmed by multiple independent lines of evidence, from the redshift of galaxies to the cosmic microwave background, to the distribution of galaxy clusters to the baryon acoustic oscillations in the large-scale structure of the cosmos. These are not speculative theories. They are observational facts supported by a mountain of data. And while our understanding of the underlying mechanisms is incomplete, particularly regarding dark energy, the observational facts themselves are not in dispute. The universe is expanding, the expansion is accelerating, and the distances between galaxies are growing faster than the speed of light. These are not things that a future theory of quantum gravity is likely to overturn. A theory of quantum gravity will need to be consistent with these observations, just as any future theory of physics will need to be consistent with them. It might reveal new phenomena at very small scales or very high energies, but it is unlikely to change the large-scale behavior of the universe, which is governed by general relativity and has been confirmed to extraordinary precision. So, while I would never say never with absolute certainty, because science is always open to revision and surprise, I would say that the probability of finding a loophole in the cosmic prison is extremely low. The barriers we face are not engineering barriers or even theoretical barriers in the usual sense. They are fundamental features of the universe, encoded in the structure of space-time itself. And while space-time might have surprises left to reveal, those surprises are more likely to confirm the prison than to open a door. Let us now turn to what I consider the most important part of this entire discussion: the philosophical and existential implications of our cosmic imprisonment. We have established, as thoroughly as possible, that humanity will almost certainly never escape the Milky Way. The distances are too vast, the speed limit is too strict, the expansion is too fast, the dark energy is too powerful, and the timescales are too long. We are trapped. The local group, at most, is our cosmic domain, and even that is so vast as to be practically untraversable. So what does it mean? What does it mean for us, as individuals and as a species, to be confined to a single galaxy in a universe of trillions? Does it diminish us? Does it render our existence meaningless? Or does it perhaps reveal something profound about the nature of meaning itself? The first thing I want to say is that the vastness of what is unreachable does not diminish the vastness of what is available to us. The Milky Way contains between 100 billion and 400 billion stars. Recent estimates suggest that there are at least as many planets as stars, and possibly far more. Within our galaxy, there are an estimated billions of planets in the habitable zone of their stars, where conditions might be right for liquid water and possibly life. The Milky Way is not a cramped cell. It is a domain so enormous that it dwarfs every adventure, every expedition, every journey of discovery in the entire history of human civilization. If we were to visit one new star system per second, every second around the clock, it would take us thousands of years just to visit all the star systems in the Milky Way. If we were to catalog every planet, every moon, every asteroid, every comet in our galaxy, the catalog would be larger than every book ever written combined by many orders of magnitude. The Milky Way is not a prison in the way that a cell is a prison. It is more like being confined to a continent so vast and so unexplored that millions of lifetimes would not suffice to see it all. And there is another perspective that I find both comforting and profound. It is the perspective offered by the French-Algerian philosopher Albert Camus, whose philosophy of the absurd speaks directly to our situation. Camus argued that human beings have an innate need for meaning, for purpose, for order. But the universe, Camus believed, is indifferent to this need. It offers no inherent meaning, no purpose, no answers to the why questions that haunt us. The confrontation between our desire for meaning and the universe's silence is what Camus called the absurd. And his response to the absurd was not despair, but rebellion. He argued that we should embrace the absurd, acknowledge the universe's indifference, and create our own meaning through the act of living fully, passionately, and defiantly. In his famous essay, The Myth of Sisyphus, Camus tells the story of Sisyphus, the figure from Greek mythology who was condemned by the gods to roll a boulder up a hill for all eternity. Every time Sisyphus reaches the top, the boulder rolls back down, and he must begin again. It is a perfect image of futility, and yet Camus concludes with the remarkable declaration: one must imagine Sisyphus happy. Not because his task is meaningful, but because the act of pushing, the act of striving, the act of engagement with the task is itself a form of meaning. Our situation is not unlike that of Sisyphus. We are confined to our galaxy, unable to escape, destined to strive against barriers that we can never break. But the striving itself, the act of exploring, of discovering, of pushing against the limits of our knowledge and our reach, is where the meaning lies. We do not need to escape the Milky Way to find purpose. We need only to explore it, to understand it, to marvel at it, to push against its boundaries, even knowing that those boundaries will not yield. The journey matters more than the destination, especially when the destination is unreachable. There is another philosophical perspective that I find relevant here, and it comes from the great astronomer Carl Sagan. In 1990, at Sagan's request, the Voyager 1 spacecraft turned its camera back toward Earth and took a photograph from a distance of about 6 billion kilometers. In that photograph, Earth appears as a tiny, pale blue dot, a pixel, barely visible against the vast blackness of space. Sagan wrote about this image with characteristic eloquence and wisdom. "Look again at that dot," he wrote. "That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. Now extend that perspective from Earth to the Milky Way. Everything humanity has ever known, everything we will ever know, every civilization that has ever arisen or will ever arise in our galaxy, every star, every planet, every possibility is contained within this single swirl of stars that we call home. The Milky Way is our pale blue dot, our mote of dust, but writ large on the canvas of the cosmos. And just as Sagan found beauty and meaning in the smallness of Earth, so too can we find beauty and meaning in the confines of our galaxy. We do not need to be everywhere to matter. We do not need to reach every galaxy to be significant. The significance lies in what we do, what we discover, what we create, what we love, within the boundaries we are given. There is also the profound and somewhat humbling recognition that we exist at a unique moment in cosmic history. As I discussed earlier, we live during a cosmological window in which the universe is still visible, still comprehensible, still full of evidence about its origin and structure and fate. Future civilizations will not have this window. They will not see the other galaxies. They will not detect the cosmic microwave background. They will not know about the Big Bang. They will live in a smaller, darker, simpler universe, and they will have no way of knowing how much they are missing. We, by contrast, can see the full picture, or at least as full a picture as any civilization will ever see. We can look out at the cosmos and understand that it is vast and expanding and full of trillions of galaxies, even though we can never visit them. We can decode the cosmic microwave background and understand the conditions of the universe just 380,000 years after the Big Bang. We can measure the expansion rate and calculate the age of the universe to within a fraction of a percent. We can detect gravitational waves from colliding black holes and merging neutron stars. We can peer into the hearts of distant stars and deduce their chemical composition. We are the cosmos knowing itself, to borrow Sagan's phrase, and the fact that we are confined to one galaxy does not diminish this extraordinary achievement. If anything, it makes it more remarkable. From a single point in an infinite universe, we have managed to deduce the laws that govern the entire cosmos. We have seen the unseeable, reached the unreachable with our minds, if not our bodies, and understood things that no future civilization may ever understand. We are the universe's witnesses, and our testimony, our science, our knowledge, is precious beyond measure.